So we'll be continuing with our class on EC303 Applied Electromagnetic Theory. So in this class we will be looking some more portion of module number 1 and we will be also looking at module number 2. Okay.
What are the things that we are going in module number 1 is we'll be looking at the magnetostatics boundary condition. And we'll also look at from module number 2 the Maxwell's equations. Okay. So we have looked upon the basics of magnetostatics in the last class, and we have defined or we have stated two laws, basically Biot-Savart's law and Ampere's law. So today we are going to look at the boundary conditions of magnetostatics. As we have seen for the electrostatics, whatever that we have derived for electrostatics is basically for a single medium. We are assuming that the medium is continuous, and it is not at all disrupted by a different medium. But when you are going to look at boundary condition, whether it is in magnetostatics or electrostatics, we say that there are two different mediums and there's a boundary between them. So what happens at the boundary, at the both side of the boundary, for the magnetic field and magnetic flux density? So that's basically the boundary conditions. So the equations that we are going to make use of for boundary conditions, the first one is basically integral b dot ds is equal to 0. And where does this equation came from? We found that the magnetic flux lines are closed, which implies that if you integrate it along the surface, it will be 0. If you integrate the magnetic flux density along the surface, it will be 0. Okay, this we have already seen in the last class. And the second equation is from Ampere's law. It says the line integral of magnetic field along a differential length is equal to, along the closed surface, is equal to the current enclosed by the surface. So we are going to make use of these two equations to derive the boundary conditions. So let's state the boundary first. As we have seen in electrostatics, let's assume that there is a boundary and the two sides of the boundary are of two different materials. Okay, so let's assume that both are of dielectric, and let's say in the first boundary we have the magnetic permeability, which is mu1. It has a magnetic field flux density B. It has a magnetic field H. So this is B1 H1. Similarly, in the lower boundary, let's say it has a magnetic permeability mu2, magnetic flux density B2, and the magnetic field H2. Okay. So the derivations for the boundary conditions is exactly same as that of in electrostatics. So I will not be going too much into detail. You can refer the video of the electrostatics to understand more. So you can resolve, so similar to electrostatics, in both the boundaries, you can resolve the magnetic flux density into two components. One is called as the tangential component, another is called as the normal component. Similarly, the magnetic field can also be expressed as the sum of the tangential component and the normal component. So in this medium, you will have tangential component of magnetic flux density B1T and the normal component of magnetic flux density V1N. So tangential component is parallel to the boundary and the normal component is perpendicular to the boundary. Similarly, in the second medium, you will have magnetic flux density is equal to the sum of magnetic flux density tangential component and the normal component of magnetic flux density. Similarly, magnetic field H2 in the second medium is equal to the tangential component of magnetic field of the second medium. Sorry, so this should be 2 because we are looking at the second medium, and the normal component of the magnetic field in the second medium. So again, here I can draw. Let me draw it in here. So you have the normal component and the tangential component. So the normal component is perpendicular to the boundary and tangential component is parallel to the boundary. Okay. So your net field is along this direction, which is basically the vector sum of normal and tangential component. Similarly, in the first medium also, the net field is the vector sum of tangential and normal components. Okay, fine. So we have set the scene. So now let's try to derive what is the relation between the magnetic flux density or magnetic field in the first medium and the magnetic flux density or the magnetic field in the second medium. So basically, what we are asking is what is the relation between B1 and B2 or H1 and H2. So that is basically our boundary conditions. Since B1 and B2 or H1 and H2 can also be represented in terms of tangential and its normal components, it is also basically the relation between its tangential and normal components. Okay, fine. So first, as in electrostatics, we are going to draw a surface. So let's assume that there is a cylindrical surface which is across both the medium. Okay, and let delta s be the area of the circular part. So let this be delta s. Okay, and remember the direction of this area is always perpendicular to the surface, away from the surface. Similarly, there is a delta S area in this surface. Okay. Let the height of this cylinder be delta H. Okay. So you can say this total is delta H. You can assume that half of its height is in one medium and other half is in other medium. So there is this boundary here in which we will have that cylinder. Okay. So here we are going to make use of the first equation, which says integral b dot ds is equal to 0. So b can be in the first medium, b1 is equal to b1t plus b1n. Now ds is basically our the surface area, which is delta s, and so I can write b dot ds is b1t plus b1n dot the delta s. Okay, but if you look at b1t dot b1s, you see that b1t is along the surface like this, and delta s along the surface perpendicular to it. So the angle between b1t and b1s is 90 degree, because of which the dot product will get vanished. So this is equal to the magnitude of b1n into delta s. We have cos 0 degree because both are in same direction. Delta s is in this direction and b1n also is in the same direction, because of which b1, the magnitude of b1n multiplied by delta s, there is cos 0 degree here, which is equal to 1. Okay, fine. This is in the first medium. So the in the first medium, this is the condition. Now you don't want to integrate because you already understood the complete value. So basically, even if you do the integration, it will be this value. Okay. Now in the second medium, so this will be b1. If you do the same integration for b2 dot ds, this is equal to b2t plus b2n, and delta s is in opposite direction. Okay, so here this is positive direction, upward direction is positive. So if you have a downward direction, it will be negative. So you have minus delta s. Again, if you consider b1, which I think I haven't drawn it here, so b1 can also be resolved into two components. b2t and b2n. This is b2. So you see that b2t is perpendicular to delta s. So delta s in this direction and b2t is in this direction. So they are perpendicular, because of which dot product vanishes. And b2n and b and delta s are in opposite directions, but they are of angle 180 degree, which is minus 1. So this you can write as the magnitude of b2n into delta s. There's a cos 180 degree which comes, so basically it is minus. So cos 0 degree because you have already taken the minus sign delta S. So you can just say it is cos 0 d. Fine. So if you add up, I can say integral b dot ds is equal to integral b1 dot ds plus integral b2 dot ds. So this is equal to, now here, because delta h is there in all the surface, we are going to make this have delta h tends to 0. Means you are making delta h tends to 0 when you do the integration, because of which whatever magnetic flux density is there along this surface will get vanished. Okay, so we'll write that. So here this is the magnitude of b1n delta s minus the magnitude of b2n delta s, that is equal to 0. Okay. Now since delta s tends to 0, all the components of B along the sides of the cylinder vanishes. Okay, so I can write the boundary conditions as B1n, the magnitude of the normal components of both the magnetic flux densities in both the mediums are continuous. So this is the first relation regarding the normal components of magnetic flux density. But I can write B1n as mu1 h1n, its magnitude, is equal to mu2 h2n, its magnitude. So this is the second relation which relates the magnetic field of the two mediums in both the boundaries. So the magnetic flux density is continuous, but the magnetic field is discontinuous because they are related by mu1 and mu2. Okay, so that is regarding the normal components. So what about the tangential components? So for tangential components, I will have a different structure to be drawn. So let me just copy this. Okay. So in this one, we will consider the magnetic field instead of the magnetic flux density. So all the assumptions remains the same. You can always resolve it into two components. But let's consider the magnetic field. And we are also going to consider different surface. And this surface has a peculiarity. So when you say it as a boundary, it means that it is not a one-dimensional figure. Okay. For example, you can have a cuboid like cubic structure like this, which is of one material, and over which there is another material placed like this, Okay, so whatever is there here is the boundary, because that is an interface. So whatever structure is what I have drawn here, it's actually a 3D structure, but I have drawn it as a 1D structure, 2D structure. Okay, so I can say that there is a part of the boundary which is extending like this, like this. Let me draw it more neatly so that you will understand it properly. Okay, so this is actually one medium, and you have another medium in this layer. So this is, so actually you will have, let's say, something like this.
Okay, fine. So this is whatever is between this, which is basically this one, is one medium, and whatever is above it, which is basically this one, is another medium. Okay, and this is the boundary. So when a current passes through this medium, usually it passes through the surface. Okay, and we also know that there is something called as a current density. Okay, and the surface current density is given as K. Now assume that the current is passing like this, parallel to the surface. Okay, so which I represent it as a cross, a circle and a cross. Okay, so a circle and a cross means the vector is into the plane of paper. And a dot is the vector is out of the plane, of paper towards you. Okay, so if you consider the vector as an arrow, the tip of the arrow will be pointing towards you if it is a dot. The back of the arrow, which is basically some stripes, which will be pointing if it is a cross. Okay, fine. So the K vector is something like this. Okay, so we are going to construct a surface like this. And with the directions as like this. Let's say this is A, B, C, D. Okay, and the K vector is in this direction. So this is the direction of K vector, which is on along the surface towards away from you. Fine. And we say that there is a vector which is normal to the surface, something like this. Okay, so I can say this can be in this direction, which is a cap n 1 2, just the name of the vector given. Fine. So this I drew just to make you understand. Your derivation might not need all these things. You can directly draw with a single line, but to make you understand, I just drew this. Fine. Okay. Now we will apply the Ampere's law on this newly drawn surface ABCD. Okay. So what is Ampere's law? The Ampere's law states that the line integral of H along dl is equal to the current enclosed. So if you consider this ABCD path, then I can say this implies the line integral of A to B H dot. Now A to B, okay, let's complete this, H dot dl plus integral B to C H dot dl plus integral C to D H dot dl plus integral D to A H dot dl is equal to the current enclosed. So what is the current enclosed in this one? It is equal to the K multiplied by the width delta W. Okay. So what is A dot dl? So integral from A to B H dot dl is equal to integral, it is basically, let's say this is H1 for A to B, B to C has both H1 and H2, we will see each one. So integral A to B H1 dot dl or A to B H1 dot dl is equal to, I can write it as H1n plus H1t dot dl is actually the length of the path, which is, let's say this is delta W and the total path here is delta H. Okay, so this is H1n plus H1t dot delta W. Now H1n is perpendicular to this path and H1t is parallel to this path. Okay, because both are tangential components. Fine. So I can write this as the magnitude of H1t multiplied by delta W. Similarly, I can write integral B to C H dot dl is equal to from B to C you have two versions. One is H1n dot H or multiplied by H by 2 plus H2n multiplied by H by 2. Okay. So I am saying that this direction is positive and this direction is positive. So downward direction is positive, rightward direction is positive, all the opposite directions are negative. You can take both the way, both are same. Similarly, I can write integral C to D H dot dl is equal to magnitude of H2t multiplied by delta W. Similarly, integral D to A H dot dl is equal to minus of h2n delta h by 2, the magnitude, plus h1n into delta h by 2. So if you add up all these things, you will get integral h dot dl. Okay. Now next we are considering that the surface is, the path is going to shrink to the boundary, which means delta h is tending to 0. So as delta h tends to 0, you will have integral h dot dl is equal to h1t magnitude multiplied by delta w minus, so there is a minus here because it is in the opposite direction, minus h2t multiplied by delta w. Okay, because this term will vanish as delta h tends to 0, this equal to 0. Similarly, this term will also vanish as delta h tends to 0, because it will get 0. And this is equal to our k into w. So I can write this as k multiplied by w. So I can write h, the magnitude of the tangential components, or the difference of the magnitude of the tangential components, is equal to the charge density or the current density or the surface current density, and this is our boundary condition. Okay. Or I can write h1t in terms of magnetic flux density. So this is b1t by mu1 minus b2t by mu2 is equal to k. So these are the magnetic boundary conditions. Also you can, in general, you can write this, both the conditions, as h1 vector minus h2 vector cross an12, which is a normal vector that we have just defined, is equal to k. So this is another way of defining the boundary conditions. Okay. So thus we have seen the magnetic and electrostatic boundary conditions, which we will use when we look at electromagnetic waves, because all these boundary conditions will come into picture. Okay. So these are the boundary conditions. I hope you have understood this. So now let's look at one more law so that we can derive the Maxwell's equations. The law is like this, or you might have already studied this law, which is called as Faraday's law. It states that the induced EMF we call as VEMF in any closed circuit is equal to the time rate of change of magnetic flux linkage by the circuit. Okay. So the very famous Faraday's law, it says that if you have a closed circuit, there is a magnetic flux or there is some magnetic field associated with the circuit, because it may be because of the external circuit, or external some material. Now, if the magnetic flux changes by time, then there is an EMF generated on the closed circuit. Okay. So, you can write this as V EMF is equal to minus d psi by dt, where psi is basically the magnetic flux. And there is a minus sign because whatever EMF is generated will oppose the magnetic field which has made its generation. So, whatever magnetic field has induced the EMF will oppose that magnetic field, because of which there is a minus sign. But we know that the V is basically the potential. So, this is basically the potential. Okay, so I can write V EMF is equal to integral E dot dl. This we have already seen along the closed path. Now, psi is magnetic flux. So, if you integrate magnetic flux density along the surface area or the surface, you will get psi. This also we have seen. Okay, because B is magnetic flux density, density is magnetic flux per unit area. So, if you multiply that with area and integrate it all towards the whole area, you will get the total flux. So, if you substitute this, you will get integral E dot dl is equal to minus d by dt of integral B dot ds. Okay, which I can write as, so remember there is a VMF, we are not giving minus sign because the EMF generated will be in the opposite direction, or the potential is in the opposite direction of the electric field. Okay, so there is no minus sign. Okay, so now, so if you get the differential inside, you will get integral S minus dou B by dou T dot ds. So, you are having a partial differentiation because the magnetic flux density can be a function of any position, for example x, y, z, and also a function of time. So, but we are differentiating only with respect to time. Fine. Okay. So, finally, my equation will get E dot dl is equal to the surface integral minus dou B by dou T dot ds. Okay. And this is my equation from Faraday's law. But we have seen that E dot dl can be written in terms of a double integral by the Stokes theorem. It says the line integral of a vector quantity is equal to the surface integral of the curl of that vector quantity. Okay. So, I can write the surface integral of del cross E dot ds is equal to the surface integral of minus dou B by dou T dot ds. So, if both LHS and RHS should be equal, then you should have del cross E is equal to minus dou B by dou T. This is actually one of the Maxwell's equation which we have derived from Faraday's law. Okay. So, all the laws, the Gauss law, the Ampere's law, the Faraday's law, and the law which says that the magnetic flux lines are closed because of which del cross B is equal to 0 will constitute the Maxwell's equation. We will see that in a moment. Okay. So before going to that, before we are going to define the Maxwell's equations, let me make you recall the Ampere's law. Okay, we saw that the Ampere's law H dot dl along the closed path is equal to I enclosed, for which we have derived this as del cross H is equal to J, where J is the volume current density. Okay, this we have already divided. Now, if you look at the identity, del cross any vector is always 0, right? So this is an identity. The dot product or the divergence of a curve is equal to 0. This we have defined in one of our classes, which says the divergence of a curve of any vector is equal to 0. Okay. So what we did, we took the divergence on LHS, which will be equal to 0, which implies del dot J is equal to 0. Okay. So we took divergence on both sides of del cross H is equal to J. Okay. So which means del dot J is equal to 0. Okay. This is perfectly fine, but there is a catch. Okay. So the catch is like this. Assume that you have a volume, some volume is here. Okay. The volume has a density J. Volume has the current density. So this is J is volume current density. Okay. Now let's say the current is coming out of the volume and no current is flowing in, the current is coming out. Current means the rate of change of charge. Okay. So I out is dq by dt. Since it is coming out, we put a minus sign. So when I comes out, whatever charge is there inside the volume will reduce because of there is a minus sign. Because when the current is coming out, the charges are pushed out. Whatever charge is there in the volume will reduce, and because of there is a minus sign. Okay. Now current is related to volume current density as integral J dot ds. So the closed integral J dot ds is equal to minus dq by dt. Now Q is related to, let's say, assume that the volume has volume charge density rho v. So Q is rho v dv. So I can write this as minus d by dt integral rho v dot dv. Let's take the differentiation inside. So this is equal to minus integral along the volume dou rho v by dou t dot dv. Fine. Okay. Now this is a surface integral. So I can apply divergence theorem to this, and I can write this as, so integral along the surface J dot ds is equal to the volume integral of del dot J dv, which is the divergence theorem, and this is equal to minus of the volume integral of dou rho v by dou t dot dv. Okay. So both sides are volume integrals. So for both LHS and RHS should have the same volume integral, then whatever term is there inside should match. So that is del dot j is equal to minus dou rho v by dou t. Now there is a contradiction. Here we say del dot j is equal to minus dou rho v by dou t, but here we proved that del dot j is equal to 0. So there is a contradiction, because of which the Ampere's law or Ampere's equation needs to be modified, and the modification is a very simple modification. The modification is like this: when you take del cross H, it is J plus another factor called as JD, okay, and JD is called displacement current density, and this displacement current density was introduced by Maxwell, and that's a major contribution to these equations, because without displacement current density you cannot combine all these equations. And displacement current density is very negligible at very low frequencies, but once it goes into the microwave range of frequencies, the displacement current density is very critical. It is as equal to J, which is J is called as conduction current density. Okay. Now, what is the value of JD? Again, let's take the divergence del dot del cross H is equal to 0. That should be equal to del dot J plus JD. Okay. So implies del dot J plus del dot JD equal to 0, but we have already proved that del dot J is minus dou rho v by dou t. So this is del dot JD is equal to minus del dot J. This is equal to dou rho v by dou t. So we have del dot JD is equal to dou rho v by dou t, but by Gauss law rho v is equal to del dot d. This we have already seen, so I can substitute this. So del dot JD is equal to dou by dou t of del dot d. Okay, so this I can write as del dot dou d by dou t. So JD, the displacement current density, is equal to dou d by dou t. So displacement current density is the rate of change of electric flux density. Fine. So it relates the magnetostatics and electrostatics using this equation. Fine. Now if you substitute this in our original equation, del cross H is equal to J plus dou d by dou t. Fine. So now we have come upon all the possible combinations of equations in electrostatics and magnetostatics, and we just need to combine to make it the Maxwell's equation. Okay. So Maxwell has coined all these laws of electrostatics and magnetostatics, which were considered as totally different fields till 1900s, he proved that you can the magnetism and the electrostatics are closely related. Once you relate them, you can see that it forms an equation of a wave which is called as electromagnetic wave. Okay, so let's summarize all these equations. Okay, let's look at each law. So this is law. Now the law can be stated in integral form and corresponding differential form. Okay, so the first law is Gauss law, which states surface integral of electric flux density is equal to the volume integral of volume charge density, and this in differential form is del dot D is equal to rho V. That's the first law that we have studied. Next, we saw that there is no isolated magnetic charge, because when we, let's say, the magnetic flux lines are closed and if you break a magnet, it will always come as north and south pole, because of which there is no isolated charge, and the integral form is integral B dot ds is equal to 0 or del dot B is equal to 0. The second one. If you look at the third one, it is from Faraday's law, which says that the line integral of the electric field is equal to the rate of change of the surface integral of magnetic flux density, or I can say del cross E is equal to minus dou B by dou T. The last one, which is from Ampere's circuital law or Ampere's circuit law, which states the line integral of H along a closed path is equal to the surface integral of J plus dou D by dou T ds, or I can say del cross H is equal to J plus dou D by dou T. Okay. So you have coined all the laws, and this laws in this collection is called as Maxwell's equations. Okay. So this law I have drawn it with a slanting line. Okay, and this is called as Maxwell's equations. Okay. So along with these laws, you should also understand the boundary conditions. Of both electrostatics and magnetostatics. Okay. So that all these terms, all these things can be combined to form a general wave equation, which we will try to solve to find out what is the waveform. Okay. So I hope you have understood the Maxwell's equations, and we have also derived the boundary conditions. So this we have basically finished module number 1, and we have also looked at the Maxwell equation in module number 2. Okay. So thank you for listening.